Also, give us your last. You got that challenge. Oh, that's one.
Yeah.
Might be graded.
Sorry, say again?
The homework one and homework two, will they be graded?
I think I asked my PA, the homework one should already graded. I saw it already graded, and homework two deadline will be 2/9 12. So after that, that will be graded over in the next 2 days, but I will the answer already put in the system, was able to see the answer after one in the end.
Yeah.
So anyway, today we're going to start a new area called the induction motor. Mainly that will be so-called AC machine system. So AC and DC machine and motor are quite different because you can see that when we talk about induction motor, this is one of the most popular AC machine. So this machine are basically we're using AC to apply to the motor, and we're not using DC at all. So when we apply to the AC system, the many things has been changed quite differently. Although the motor system, we tend to use the three-phase, but of course, single-phase induction motor also feasible. How much have you learned about the three-phase system? Have you all learned three-phase? Not at all? No.
Self-study.
Self-study. When are you going to learn the three-phase system? You don't know. The circuit three-way only single-phase. And then here you learn some three-phase. But in the future, you'll also learn the AC and RF. That's more in the three-phase. Circuit system, I think you learn briefly about single phase, you won't cover too much on three phase. So we do have another course. I don't remember the title will be for AC and RF. That will be more for the three phase system. But anyway, in here, we do need to use some knowledge, but try not to use that much. I just assume the motor will be, say, single phase first. The concept will be the same because for any motor, three phase and single phase, we just putting three of them together in 120 degrees away from each other. So in here, we can also show you how to learn the AC motor properly, even though we start a concept for three-phase system. So today we're going to show you about the basic configuration for induction motor. Then you see how they look like, how the DC motor are different from the DC motor, AC motors, and then how the circuit look like, the equivalent circuitry, some formulation, basic formulation, and then you also try to learn more about the rotor and stator, how they shall look like. So the configuration are quite different. So a lot of the special design over there. So here will be, anybody can tell me what's the meaning for induction motor? What's the induction motor? Have you heard about that? Why we call induction? Any thought about induction motor? Just when you see this name called induction motor, what can you think of? Using induction, yeah. Basically, something using induction is the main concept to make the motor rotate, turn, right? And do you think this kind of motor must be powered by motor driver, or just can power by simply AC from our power point, from our main distribution? What kind of AC waveform we needed? Can we just plug the motor into our power system, power distribution to make it work? Or we do need some power electronic driver to do that? What do you think?
Battery inverter.
Yeah, battery inverter, okay. Yeah, today we mostly to drive all the induction motor by saying, say, battery or DC. through inverter and then to the motor. But that's not the case. Many of induction motor can directly connect to an AC system without any control. In this case, we just want it as without any control. Then of course we don't have too much capability like the torque control, speed control. You may change vary with the load demand. For instance, when you drive the motor at heavy load, then the speed may reduce slightly. Then in this case, that may not be too good. So we do need to have a motor driver, but that is not the case. We can control it, can connect purely AC, that also works. That is why induction motor was so famous, popular. Many years ago, when we firstly developed induction motor, we don't have power electronics. You can see, imagine 40 years ago when we don't have power electronics, how do we control them? We just control by purely some really special manner, maybe simple electronic to control them. We're still able to connect a motor together with a single phase or three phase system. The motor can still run without any problem. And then AC motor and DC motor, which one is better? Any thinking about that?
Depends.
Depends. Depends many. Right. Or any feature you may think DC motor could be better than AC motor?
Cost.
Or would you like to say something? Cost?
Cheaper to make.
Cheaper to make.
You don't need to control it for.
No. What else?
Simpler.
Which one is simpler? DC or DC simpler? Yeah, DC is much simpler.
I think it's more controllability.
That's the key thing. DC are more controllability. As you see from the last lecture, we can able to control the speed and the torque quite separately, quite easily. Just control the voltage, control the thrust, we're able to control it. For AC motor, you can see that we injecting the system using three-phase voltage. That three-phase voltage, we don't know what is the voltage. We don't know what the magnetic flux is. We don't know how to control the torque. We are kind of the interpretation, how to relay the AC voltage to control the motor torque and the speed. So the control point will that'll be more complicated, not an easy job to do, right? So that's why I think I should say a DC motor, main thing is better than AC will be the control. And then you can say, oh, DC motor can be low cost than AC. Hard to say because there's so many manufacturers. Today, DC motor and AC motor are both under the mass production, fully mature technology. They're all really low cost. Of course, DC motor, we do have a problem. If we use the PM, permanent magnet, then it will be expensive. But if we use the separately excited, then the cost also quite low. So the cost is quite hard to say. They both are really low cost anyway. So which type of induction motor are commonly used? So, but of course, when I ask you this question, you need to know how many different types of induction motor. What are they? Yeah, probably you don't know. You're going to see the answer in the next few pages. Market share. What do you think? Market share. Do you think induction motor have a good market share as compared to DC motor? No. Well, they both. Yeah, you like to say something?
Circuits where the AC motors used before power electronics, or do we still use these with power?
Both AC motors and DC motors, we already there before we had the power electronics. Because both of them can be energized without any power electronics. We connect a pure AC source to an induction motor, it's still. Of course, we need power electronics more control. We can control the speed, we can control the torque. Same as DC motor as well. You can also control pure DC. You can also run, but we can using variable voltage, variable field current. We can control the torque and the speed. So in here, the market share certainly both DC motor and AC motor have a really large market share. I guess AC motor, like the induction motor, have more than 50% of market share for all the motors because the AC motor can be used for many applications, like in all the building. You have not the AC motor for the pump, for the elevator, escalator, and also we have the power regeneration, like the wind turbine system, and like electric vehicle, we also use that. So that's another application. Market share will be quite large.
And this is that, like, the AC motor would be, you would usually use an AC motor trying to be connected to the power grid or use functionally, like a washing machine or, like you said, elevators, turbines, and like power generation, as what a DC motor would be anything kind of like anything where you would usually move something like, toy cars, anything that uses DC batteries.
Well, and when they all the system we connect existing power grid, most of it, they want to direct online, they usually would be the AC motors like the pump system. Simple in the building menu of the pump system. You don't need to control that. We just on and off. You don't need to use inverter, mainly because of the cost. If you connect motor, then simply on and off, that will be good enough. But it will be for more and environmental friendly systems, they can use inverter to control the motor to have a so-called variable speed control. And for some DC motor, for instance, for some power drill, we use DC motor because really low cost and quite small size. DC motor, when we use the PM permanent, the power density can be really, really high because we don't need any additional circuitry to generate magnetic flux. So that the size can be quite complex, high power density. So that's why for portable device like the portable pump tools that we can use it. And then for some stationary tool, then you can use AC motor or those DC motor with a separate side field. So that means the application are quite varied, depending on your application, the cost, and the market availability. It's hard to say which is better than which one, but they're all widely available. So this statement may not be really a good statement to answer your question, but you can see that anyway, the industrial motor do have a very large market share. If you check the literature, some of them can say, oh, they have 70% of market share. Some other website, they only get 40%. But I think something like 50% would be quite reasonable to say the industrial motor has such a big market share, mainly because they are low cost, highly mature. We can just connect them to AC without any power electronic. It also work. Of course, if you put in power electronic, we can able to control more about your capability, like the torque and the speed or the transient operation. So like say the electric vehicle, we also use the industrial motor for that. Inside the electric vehicle, we do a battery through an inverter and convert the AC signal to control the industrial motor. That also work. Of course, many years ago, we do use the DC motor for EV. During that time, we just using pure DC motor. Why is that? Because DC motor will be just we connect them into DC battery that can join. So in the old time, we tend to use more the DC motor for the EV design. But today, we tend to go for lower cost. Then many of them are using AC join to drive the industrial motor. So anyway, today we're going to discuss a number of items, including some introduction, and then we talk about the stator and about the rotor, and also difference between industrial motor and DC motor. We're also talking about the operation. So there's a few items. So this lecture mainly talk about some introduction. We don't try to introduce too much theory or too much formulation here. Just go through a few descriptions so that you understand more about the industrial motor, how they really look like. I know that topic getting harder to you because probably in your physics, you may learn some electromagnetic, you may learn some basic DC motor, right? I think many of you have learned something DC motor before, but I don't think you learn anything about AC motor in physics. So that's something new for you. The configuration there will be also quite complicated, but try to make it simple. So first of all, market share. I think, as I mentioned before, the market share are quite varied. Sometimes can say go up to 70, 80%, but sometimes 65. But to say for industrial drive, I'm not talking about the global motor system. For industrial drive, then that can go up to 65%. That means those drive has been used in the factory, like in the assembly line, like in the delivery and track system. And so they tend to use more of the industrial motor, mainly because all powered by the AC system. So, I mean, that would be something at least 65%. Of course, for electric vehicle, then there will be another story. So that is not quite industrial drive system. There will be another type of the application. They are called mobility system. So, but anyway, most of the industrial drive tend to use more in AC motor, mainly about the low cost. We don't need any permanent magnet. So that's why in a way will be quite straightforward. And then we don't need to worry about the contact, the commutator. DC motor, we do a commutator and carbon brush problem. So there will be eventually the contact point will age, we need to change the component. But for AC motor, we don't need any contact, electrical contact to the rotating part. So in this case, we can make the motor can last for ages. Yes?
About brushless DC motor.
Yes, that will be next few month. Next month, we're going to discuss about the brushless DC motor. This is another new story. We're going to look into that. This is a more latest technology. Brushless DC motor will become after the industrial motor. This technology roughly about, say, 25 years. Technology, industrial motor, at least 50, 60, probably maybe 70 years. Since we got the AC motor, since we have the Faraday's law, then we started to develop the AC motor. So for the application, we see that application can vary so much, like the manufacturing plant, as I say, the assembly line, we tend to use a lot of the AC motor, then robotic system, we also use them. Robotic system, I didn't mean is the humanoid robot. I mean the robot used the factory. Then we tend to use a lot of the industrial motor. And renewable energy, mainly about wind turbine, we 100%, not 100%, I think maybe 80%, 90%, we tend to use industrial motor. And it's really good because mainly the power output will be AC. So when we use this kind of industrial motor, we can able to generate AC voltage directly, then we can connect to the power grid. And transportation system, like the train and also the electric vehicle. I think in the old day, we still use a lot of DC motor, but nowadays gradually we move on to AC motor, mainly because we are able to develop a new method of the control the motor. You see, before when we tend to use more DC motor, mainly will be control for DC motor will be simple. We can control the motor thrust, motor torque, motor speed quite easily using armature current or the field current. And then when we started to use AC motor, I know it's much easier to do. There's no contact point problem, no commutator, but the control will be complicated. But 25 years ago, we started to develop a new method called vector control. Probably you haven't heard about that, called vector control. That is another new method we're able to control the motor. The vector control able to control AC motor like a DC motor. So that's why we developed this method. We are able to control it. So that's why we started to use the AC motor again. Something really similar to the industrial, similar method to control the DC motor. And then for the home application, like the heating, ventilation, and air conditioning system, we tend to use a lot of the industrial motor. The whole infrastructure for building, like the compressor, pump, and fans, that will also popular devices being used. So you can see that industrial motor are really popular, has been used for quite often for most of the rotating part. So I should say the industrial motor is one of the beauty development we have been using since we have the mobility system. So first thing, the engineering is quite elegant. Later on, when we see the structure, you can see that, oh, the design is quite good looking, quite elegantly being designed. And at least the development are quite low cost. We don't need like the DC motor, we don't unlock the part. Like the part in DC motor with the PM, commutator, unlock the contact point, anything, any moving part with contact problem, we don't quite like it because it doesn't last for a long time. So that's why DC motor usually after a few years, 2 years, probably you need to change the carbon brush. That may not be too good. But for industrial motor, many industrial motor, industrial drive have been used in the market for more than 10 years, 20 years without any maintenance. That is why you can see that for EV, probably you don't need to have any maintenance to the motor, even though EV is 10 years. Yeah. But for engine, you need to have a good maintenance every few years. So that's why reliable, low cost, and robust, and no carbon brush, no PM. So that's why maintenance will be minimum. So the principle is also quite straightforward. It basically depends on the Faraday's law. So later on, I think we'll go through more about what it is. And the motor, mainly, we tend to use more three-phase motor because three-phase balancing, especially for large motor, must be using three-phase. For low power motor, we may tend to use single phase. Maybe for a few hundred watt, maybe tens of watt, we tend to use single phase. But single phase do have some problem, how to start the motor, how to make it balance, also have some kind of the issue too. So both of them will be coexist. I think for the future development, because we got a lot of automation and power system development, EV development, even the aerospace, we tend to use a lot of AC motor. And then for industrial robotic system, we tend to use them. Hydropower, wind power, also very common to use the industrial motor. So that's why I can see that why industrial motor getting so popular, because it match really well with a number of the application. So here is just show you how they look like. That's a really rough drawing, not really detailed. Obviously, we got something to cover them. And then we also have the internal disc cover that will stator. Stator means, I think you know, it's not rotating. So stator usually will be our copper winding. Inside there's another copper winding to provide excitation. So the stator will mainly to generate some magnetic flux in that circumference, in that cylinder location. And then the moving part is the rotor. So there's also some winding on there. So this winding and this winding will interact together with producing some kind of the so-called torque, magnetic torque. And the stator inside, they have three-phase system, or of course single phase also be available. They have a rotating magnetic flux inside. So the flux look like inside rotating in the same kind of frequency as the AC input. So it doesn't like the DC. DC will be constant flux. The flux is not moving, but the AC system, the flux will rotate in the same frequency as the input AC. So that's quite interesting. The rotating part, we call the rotor. Then that will be inside this cylinder. It's also usually cylindrical. And the inside, there's some kind of the magnetic turn as well. Later on, we talk about how they look like. And also have the enclosure. So typically, this configuration are quite straightforward. You can see that we don't have any connection in the rotor. Of course, only for this particular industrial motor. We do have some other industrial motor do have connection in the rotor part, but bear in mind, and for this lecture or the next few lecture, we try to focus on the industrial motor without any connection from here. So you can see that without any connection from the rotor, then we can eliminate all the common brush and also commutator. So you can see the motor will be much easier for the various application, high power, high current. We don't need to worry anything about the contact problem. We don't need to worry about any mechanical wearing. So in this case, the motor can able to work by itself without too much maintenance. So here will be more detail with some color photo. You can see that. You see all this kind of configuration, we do the thermal management. So some of them you can see that we have our cooling frames usually attached to the motor like this. So you see a motor getting quite hot, especially for this kind of the winding. You got high current pass through them. The rotor also high current, then while rotating generate heat. Then in this case, we can use, once rotating, we can use the rotating method to work with the fans to help us with the cooling, become the forced cooling net. So you can see that this motor, we call it screw cage. So screw cage is one of the most famous industrial motor. Most of the industrial drive tend to use this one. So why we do that, next few pages, we will say why it looks like screw cage. And of course, in here, we had the stator. Inside, we got this rotor. So the total configuration will be just that. Of course, for this winding here, we also use magnetic core, like the transformer core. But in here, we do have some kind of the silicon steel core inside to help us with the metallization. Similarly, for the rotor as well, beside the rotor turn in here, inside we also have the magnetic core in. So both of them will be just as simple structure as this. So you can see that we don't have any complicated structure. We don't need to use PM, only copper winding on both stator and rotor. But of course, we try to make them in some special manner, able to generate magnetic flux inside this cylinder, and then that's so-called the rotating magnetic flux, being able to interact with this rotor to generate the torque. So that's roughly about how they look like. The good thing is we only input the power to the stator. We don't need to input anything to the rotor. So that means the 3 wire from the 3 phase or 2 wire from the single phase, we only connect to all the wiring here. We don't need to connect anything here. So that's why the total design will be simple. We don't need to worry anything about mechanical connection, especially inside the rotor. So here you have some picture. You can see that we do have the bearing to holding the rotor system. We have the cooling fans, have with the cooling, and then we have a stator winding like that. The stator winding, you can see that the wire on the metal core, the metal core do have some lamination. As you mentioned before, we mentioned before, all the metal core do have the lamination to reduce the eddy current loss or magnetic losses. Just like all the transformer as well, you can see a lot of the lamination inside the transformer. So that's roughly about zero. So the inside the rotor is called a screw cage because the rotor really look like a screw cage. So later on we'll show you why it look like as such. So let's first of all look into the outer frame. That means the stator. So that's how the stator look like. So you can see that in here, you a lot of the stator winding here. How to do the winding? We have some special manner to look into that. But key thing you can see that that's mainly the stationary part, fixed component. We don't need to rotate anything. But however, when we energize all this later on, we see some diagram how we put the winding there. The winding will three-phase winding. The winding itself will be displayed by 120 degrees from each other. So that's why when we energize them, they are moving in sideways manner. Then next, we can see the magnetic field inside here will also so-called the rotating magnetic flux. So the flux will rotating continuously around here. So that will create the variation in the flux to interact with the rotor winding to create the torque. So it may not be very clear here. So the winding here, I'm winding on this magnetic core. You can still see the magnetic core. You can see the lamination here. Many pieces of the silicon steel become lamination. You see the lamination, each of them have a bit of the coating, varnish coating to isolate each of the lamination from each other. So there won't be any direct contact. So that means the lamination is not just purely metal sheet, but each of the metal sheet will be isolated with a coating. So this one and the next one and following one will not have electrical connection, only a magnetic connection. Magnetic flux can go through that. So that's why you can still create the suitable magnetization, but electrical current cannot go through the lamination. There's some kind of theory, what kind of lamination we need with the lamination doing this or doing that. So that all depends on how the eddy current being flow. But we're not covering here how to design them. Probably that will cover in other classes like the electromagnetics. But here you know that inside the stator, we do have a number of the lamination to stop eddy current. And then the lamination, the thickness lamination will according to the skin depth for the design. If you go to any website, you can see the skin depth is highly related to the frequency of operation. The low frequency, then skin depth will be thicker. At high frequency, skin depth can be less than 0.0 something mm. But for our frequency, we use here 50 to 60 hertz. I don't remember the skin depth properly in terms of the millimeter. This kind of the, what is that? Okay, not very good control anyway. So the lamination mainly is to reduce the eddy current losses to improve the efficiency. So that's true for all the transformer and all the motor. So we do have lamination. If you do a you have got any old motor or home motor on your scrap yard, then you can able to get a motor to check inside. You can see there's a lot of lamination there. So remember, all the lamination are insulated from each other by some varnish. So that is to say, you can see that the stator consists of the main component, like the outer frame for that kind of outer frame for the protection, protect it from the whole housing, and also all the internal part. So for large motor, we will fabricate from separate pieces, maybe a frame. For small motor, then we have using the casting, we can make the frame together with the magnetic core together. So the stator core mainly about the lamination. That means we show you just now. So when we do the winding, we do have the slot there. Slot is you can see there's another slot here. And then we put the winding here. The winding will go through that kind of slot. So you can see that inside the stator, there's many slots there. We can able to use the slot to embed with the winding there. So the winding able to embed inside will not have any contact to the rotating part. If you put the winding outside the core, impossible because you can stop the rotation. So that's why the term slot, you should understand that the slot is something inside the core, then you can able to put the winding there. Yeah, that's the winding. So for instance, there's a stator. Then you can see that the slot usually just able to fit in with the winding, and then we using some of the epoxy to fix them so that it won't become loose. So each of the stator winding are of course using copper winding. Each of the copper wire are also each wire are also enamel coated. They are also isolated. Just like when you make the transformer in the lab, all the copper wire, they are enamel coated. So even though you put many turns there, each of the turns will not touch each other because they are all isolated. And then all this winding will connect to the three-phase voltage. Like you got phase A, phase B, and phase C on the stator, and they all will connect to the AC power source in different kind of three-phase manner. Later on, we'll discuss them we can connect them in delta or star. So that's another way we can connect the motors. And then another thing I'd like to introduce to you is the poles. You see, for a magnetic motor, we can arrange the metal winding into different poles. We don't use a single magnetic wire to one of the phase. So you can imagine, for instance, before we have three-phase motor, you can connect them into three-phase. So you got the phase A, B, C. So you may imagine, oh, there will be only one winding for each phase, but that may not be the case because somehow one of them, we can divide them into maybe two windings in the circumference of the stator. So in this case, that will become two windings for each one. Then we can arrange them. So for instance, there's here, then one winding. You can arrange one winding here, and then later on we can arrange another winding here. So you can arrange the winding rather than a single winding, but more than one winding. That would therefore create different poles. You see, one winding here, we got two poles, one pole here, one pole here. If single winding, we only have two poles because there's a beginning and end of the pole. But if you use two winding here, one winding, two winding, that will become four poles. So here will become one pole. So all depends on how we want to arrange how many winding to construct one of phase. So that's why we introduce a term to you of poles. So the pole is not just like the rod we are doing, it's mainly about magnetic winding with harmonic magnetic winding to make up each of the phase. So when we energize them, we can therefore create two winding. Each winding have north, south, and north, south for this north, south pole arrangement. In order to make some special method when we try to rotate a motor. Later on, we can see how we're able to use different poles to excite on a motor to make the motor can rotate slower than before. You can see that if a motor, we have three phases in here. Each time we energize that, it rotate from here to that 120 degree for single winding for two poles. But however, if now then you try to make them into two winding here, one winding, another winding in the other side, then we have 6 winding here. Then each time the motor only will rotate half of the 120 degree. Each time we only progress for one winding. And then next excitation, you also progress to the next winding. So that means putting more winding there, we are able to make the motor to rotate slower. So later on, I'll show you how they look like. But basically, you can see that the number of pole here, so here we have 4 pole when we use 2 winding, and 2 poles when we use 1 winding. So basically, how we understand the number of pole we use in the induction motor. So basically, you may not able to see the pole properly in the metal core, then because you can see many winding there. But the way we connect the winding there, we're able to make more than 1 poles. Yeah. The number of poles usually for 1 winding, we got 2 poles. Right? 2 winding, we got 4 poles. And 6 winding for per phase, we got 6 poles. So we're putting them on the stator slot in order to create various way to how the thrust are being rotated in the stator. So to do this one, we can therefore connect all the coil in some special manner. So you can see that all the winding can group into different manner in order to produce more number of poles. So in theory, if you want a high-speed motor, then we only use 2-pole machine to do that. Then we have 4 poles. Later on, you can see that we are able to reduce the speed by half. Because every time all the injected voltage, we need to pass through 1 pole. Next time when we have another sideways cycle, you go to the next winding and so on. So we can use the diagram, we can see much easier how they look like. For instance, this diagram is a 2-pole stator and single phase. We seldom use single phase for induction motor, but yeah, draw this diagram to you so that you know how they look like. So now then we got 2 pole, 1 pole, 2 pole. We got 2 types of the winding here. So that means in here, when we excite them, you create a 360-degree rotation. So that is how the 2-pole machine shall look like. So you can imagine here, then we got probably the south pole here and north pole here. So that will create, but this first is rotating. Sinusoidally rotating, just like the DC. DC will be fixed because it is rotating. Then this first will therefore pass through the rotor there and create induction in the rotor. So this variating thrust will create induction in the rotor. So, and then the rotor will therefore create its own magnetic thrust. So these 2 thrusts interact together will therefore produce the magnetic force. So basically how you look like. So you can see that if for simple single-phase motor system, then we have 2 poles will look like in such a way. So each time we got south and north, so we create 2 poles for us to interact with the rotor winding. But bear in mind, this motor does not exist. I just illustrate to you how the meaning for 2-pole machine, single-phase system. If this going to for 3-phase, then we're able to rotate the motor properly. But in here, if single phase, then we'll only have 2 poles. But if 3-phase, we repeat this for another 2 more times, become a 3-phase motor. Arrange them in 120 degrees apart from each other. But here for two-pole machine will be basically look like this. So basically you can see that we create a magnetic flux between the poles. Then this magnetic flux will generate. So the inside here will be the rotor bar, the so-called the motor winding. So when we have chain of magnetic flux pass through this winding, you create its own induction inside the winding here. So this winding inside will also create magnetic flux. So these two magnetic flux will interact to each other. They will show the opposition. Then you're able to rotate the rotor inside this moving part. So that roughly about how it look like. Of course, the detailed operation we need to go for the geometric equation to understand more properly. But here you can see that the structure would basically using this method to have excitation to the stator, and then we get a rotating magnetic flux, and then that rotating magnetic flux will interact to the rotor. The rotor will create its own magnetic flux, and then these two interact together can keep the rotor to rotate. So this is the simple two-pole stator. But I have a remark here. This is not working in theory. It just shows you how a two-pole machine look like. Here, but we do have single-phase two-pole machine exist. How it work will be we need to have additional coil here, so-called the startup coil, to create a method for the motor to rotate. Then once the motor has already started the rotation, we can turn off the additional winding to have the startup. So we can able to make a startup coil here. So somehow we have a startup coil to create the initial magnetic flux to drive the motor. Because as just two-pole machine, you're not able to always start the motor properly, depend on the motor rotation location. So all the single-phase motor, we do the startup coil to create another 90 degree. So these two produce 90 degree flux so that we're able to start the motor. But that part is not covered here. So we just show you this is a basic principle how the single-phase motor look like. And then four-pole machine will be much easier to understood. You can see that how we're able to create a four-pole machine here. So now then we got four-pole. Obviously, you can see the four-pole here. So we got so single phase attached to here. All the winding are connected in series in such a way. Then you can see that if we use our hand, then you can see that. Then that will be, I think it's north, south, north, south. So these are arranged in such a symmetrical manner. So much more symmetrical than the previously two poles. Previous two poles, they are not symmetrical, so really difficult to make sure the motor can rotate. But now then we are more symmetrical, arrange them in 90 degrees to each other. So in this case, so this rotating magnetic flux all around the 360 degree, we're able to interact with the rotor internally, you create the rotation. So four-pole machine will be available. We don't need any special startup circuit to assist the starting and also the rotation. So that's how it look like. And then we can also go into the three-phase system. For three-phase system, for example, I use three type of color to represent the three-phase, red, brown, and blue to represent three-phase. So for two-pole machine, we still, each of phase, we have two poles. So two poles in here, two poles in here, and two poles in here. So each of them will therefore create its own rotating magnetic flux. So all the three phase together will become the three-phase rotating magnetic flux. So if we go a bit further, then for the four poles, we just repeating the four poles just now. For west phase, you got 1, 2, 3, 4. And then we also have another phase brown. We got 1, 2, 3, 4, and so on. So that are arranged in this manner. So obviously you can see that when we increase the number of input phase, But usually for AC, we only have single phase or three phase. We seldom use other phases. And then when we go for 4 poles, then this motor will have a more stable and less torque ripple, and the rotation will be more smooth as compared to this kind of the single phase. So we got more number of poles here, total number here will make the motor rotation will be smoother. So that's how we understood the system. Any question up to this point?
Yeah, on the right-hand side, for the four poles left, does that mean like more poles it is, that it takes more energy to control, or?
Certainly, because well, it's a three-phase system. Each phase you will be energized. For example, red phase, L1 phase, all the regular will be connected in series to produce with all the 4 coils are connected in series. So, and then similar for the blue phase and the brown phase. Then to use more energy, I don't think so. As I mentioned before, you don't need any additional control electronic.
Oh,
You just separate winding, you just single winding. Long winding become 4 winding.
so it just gives you more stable turning.
That's a good point. You see, when you compare with this one, we only have one winding, 2 winding for each phase. But this one we separate into 4 winding. Of course, the workmanship will be much more, but the motor will become smoother, less ripple, more stable, more symmetrical. But by doing this one, then each time the motor will move. So if we got 300 for this thing, when we have one sideway applied to here, the rotor will rotate probably 1 cycle. But for here, then it's not the case. When we have sideway applied to here, you only move from here to here. That's all, 1 cycle. And then for next cycle, you move from here to here. So each time, the rotation only move between 2 poles. So that's why by using the winding sum method, you can actually, although you make the motor more symmetrical, smoother, more stable, but the motor will move lower, 50% of the speed.
So, what about using power electronics? This is your only way of slowing down, of controlling your rotating speed on your AC motor.
That's a really good question. All this motor we have been talking about here can be controlled without any power electronics. I draw a sideway here to say if it naturally apply a sideway to its motor, that's how the motor works. Yeah. But however, when we use power electronic like this, you see this motor, if we use 60 Hertz, the speed of the motor roughly will become 3600 RPM, right? So that's standard for all the 60 Hertz motor. And then when we use 4 pole will be 1800 RPM. Then 1800 RPM still really high speed for each vehicle. You never see the wheel can rotate 1800. The wheel only rotate 200 RPM. That would be really high, 300. So even though we say I reduce the speed, that's still too high. Then when we use power electronic, we use another method. We can further use so-called variable speed drive to further reduce the motor speed or further control the motor speed and torque with the power electronic to control that. So although I say 4 poles reduce the speed, I don't think there's any issue. I really like the motor have lower speed. Unless you want to go for other special application, if some high-speed robotic system, you really like high speed. Or then for instance, wind power generation, you can see that the wind turbine, the rotation speed only 100 RPM. You never see the wind turbine rotate just like, wow, a few thousand, impossible. They only rotate maybe 1 second per cycle. So 100 RPM, 200 RPM is quite a maximum for wind turbine. So using this kind of the 3-phase motor, 4 poles still too high speed. many of the wind turbine hydropower, then the speed will be, number of poles will be even higher. The high number of poles, of course, you need to think about the construction, much more expensive. Firstly, you need to put so many, so that's called the slot, yeah. You got so many slots here. So when you make the stator, you need to build in many slots to build all the winding there. So the workmanship will be more complicated. You need to separate many winding instead of single wire, but you need to separate the many winding there. And then between the winding here, you need the connection. You need to connect them up here. In here, you can see that this need to connect to here, this connect to here. All the winding connection will be quite complicated. So that's why, but of course, when you talk about mass production, we don't care. Mass production, the machine will do all the job for you. So probably may not be an issue. But in old day, 50 years ago, when we do the induction motor by hand, then that would be cost quite a lot of the work. But today, when we use mass production, everything will be fabricated, may not be an issue. So that's why today, when we produce induction motor, they're really low cost. 4-pole, 6-pole, whatever pole is quite not a problem. For hydropower, wind power, the number of poles will be many because they want to reduce the speed. They don't like to use gearbox. As we mentioned many times, we like everything without any gearbox, only use power electronics to control the speed. So like this motor, if you can make a motor with many number of poles, you can reduce the speed. We don't need to use any gearbox because the gearbox actually more look like embedded inside the number of poles here. So actually we have gearbox, but become magnetic gearbox inside all these number of poles. So that's a beauty for electrical machine. We eliminate all the mechanical part. We don't like mechanical because we are electrical engineer, right? Anyway, so that's how it look like anyway. The good thing is we don't need any lubrication, we don't need any gearbox, so the maintenance would be minimal. So for electric motor like this, you can able to use for 10 years, 20 years without any problem. Like in your home, many of your AC or your refrigerator, if they use AC motor, you don't need any service. They can use for many years. You sometimes may see some electronic broken, but not the motor. The motor usually can last for a long time. Anyway, 6 pole, you can see that now we go up to more number of poles. Yeah. Of course, that's a more exaggerating. So in fact, the actual motor, the slot here, the slot not that deep, it's only a little bit. Oh, you can very shallow. It's not, but here I just draw it exaggerating so that the actual motor is much not that deep. The slot area are much smaller. Just able to put the winding. Okay. So here the remark will be the number of pole of course will be even number. We don't have odd number because two winding must two turn, right? Beginning and end. So all the number of pole must be even number. So 4-pole and 6-pole are more common for industrial drive. But of course, when you go for hydropower, wind turbine, then we may need to use more number of poles. Yeah. 2-pole is okay, but high risk pole. But of course, for really low cost machine like simple pump system, simple motor, then we also have 2-pole machine too. So 2-pole machine for single phase may not able to start properly because somehow when you energize them, you just don't start. You need to have the rotations. Then we do have a starter coil at 90 degrees to have the starting. So that's also commonly being used for start some simple motor like 2-pole machine. So, and then to conclude what we have learned just now, you can say the stator we usually try to construct with a number of poles, not only 2-pole, 4-pole, 6-pole, many poles will be available. For a lot more poles, then the motor speed will be lower. So that's the basic configuration. So that so today, if you go to any specification of any motor, maybe tonight you check the internet, you can see how the motors are being available. So one of the parameters will be number of poles, right? 2-pole machine, 4-pole, whatever. Then you can see roughly the speed will be inversely proportional to the number of poles. So that's how it look like. Any question up to this point? So here we'll further explain to you how we able to understand the number of pole. So that means for two-mode machine, you just go through from north to south and then going backward. So every time going backward. So one sideways, then you just go north to south and then backward. So that's how you look like for one complete AC cycle. And for four-pole, then you go each time for each 90 degree. Yeah, so that's why it will become reduce the speed. So typically for 60 Hz system, the standard base frequency, we call it base frequency or frequency, will be 3,600 RPM. Do you know how to calculate 60 Hz? Convert into 3,600 RPM. I think you all know that. So that means two pole will be 3,600 and four pole instead of 1,800 and so on. So that's how we use number of pole to understand more about the base speed anyway. So you can see that when we use more number of poles, the rotating front inside will rotate slowly because each time you only go from this set of coil to next set of coil. You won't go through everything. So that's why you can see that we can able to number of poles to control the rotor. So you look like the rotating thrust dragging the rotor slowly because we putting more number of poles. We make the rotation thrust moving slowly. So that's how we try to do that. So we have been talking about rotating magnetic thrust for quite a while. So that's how it look like. Say we got a three-phase machine, the three-phase voltage, although we haven't learned the three-phase voltage, but don't worry too much about it. Imagine the three-phase voltage, just like the three-phase, like that, each are separated by 120 degrees. So you can see that the voltage going up and down in such a way. So when we energize each of the coil in this three-phase manner, the applied voltage will of course generate magnetic thrust. This magnetic thrust you can imagine will moving in the sideways manner. So peak value at here, and then after moving with the amplitude with the time like that, and after 180 cycle, then you go to this maximum and so on. And then the other phase will also do like that. So you can see that the magnetic thrust inside will, when we have three phase adding together, look like the thrust will be moving this maximum, this maximum, this maximum, and this maximum, maximum, maximum. So it look like the thrust will rotating. The peak value of thrust will all rotating within the cycle in this kind of the thrust manner. So of course, the thrust is not actually moving, but you can imagine the amplitude of the thrust in here, this point will be maximum. Next phase will go to this maximum, so look like the thrust are moving in this phase. So so that's why we call them the rotating magnetic thrust. That's how they really look like. We're not using a machine to rotate them. We're just using AC voltage to make the amplitude moving in this circle in this manner. So you can see that because the sine wave are moving continuously, the magnetic thrust in here more look like are rotating continuously in such a manner. So once we got rotating thrust, the rotating thrust will interact with the rotor inside to produce our associated torque. So that's how the system look like. So we have done something about the stator now. Let's see how the rotor look like. The rotor are quite different from the stator. The usual stator, we try to generate magnetic thrust. So there were many number of turns. So not only single turn, but many, 100 turns, 200 turns, depend on the magnetization needed. But the rotor is different. The rotor actual number of turns would be much, much less. So later on, now we can going to see how they look like. So if you see the structure, the rotor actually we cannot really the winding. Don't imagine the rotor have many of the coil like this, many coil, 100 turn, 20 turn. That's not the case. Usually number of turn will be just one turn, two turn. The inside, they only using bar, so-called the copper bar or maybe aluminum bar to make up the rotor winding. So do I have a picture? Something like that. These are also the magnetic, the copper or aluminum bar to make up the motor winding. So you can see how it look like. We do have magnetic core inside. Each of the core has also have the lamination, a kind of the pieces in here, do not allow the eddy current to pass through them. But we do have the motor winding that is hooked up to the motor winding, so only have single turn in the rotor winding in such a way. They all have a short circuit turn, so we don't have many turns. Each turn already short circuit. They don't allow the turn to go through many runs to make up. So that's how they look like. So all the bars are so-called longitudinal, so that means they are going in such a way. We have an end plate, end ring here to connect them up together. So like end ring, connect both ends of the rotor. So electrically, you can see they are more look like a short circuit. So each turn we don't have, so all the turns are shorted together. So more look like the rotor have always has one turn. So how they look like. So the lamination also important. Inside the lamination all important because inside here there's also high magnetic flux produced by the stator and also the rotor. So the flux internal will be quite high magnetic flux. So you create a high eddy current losses. So that means the lamination here also quite important. But the frequency inside the rotor will be quite special. Anybody can tell me what do you think the frequency of current inside the rotor? Anybody can imagine or tell me more about that? What do you think? Do you think that if we exciting the external from the stator 60 Hertz, what do you think the frequency inside the current inside is? Do you think they have 60 Hertz, 59 Hertz, 50 Hertz, 30 Hertz, 1 Hertz, 2 Hertz? What do you think? Any comment?
60.
60? You think the rotor current inside will be 60 Hertz? Any other thinking? What do you think? I'm sorry, say again? Less than. How much less than? Later on, we'll discuss further about the rotor current. The rotor current inside actually is not running at 60 Hertz. Even though we are inputting 60 Hertz, we run at another frequency of the current. So that's a quite special about that. The frequency inside will much lower, only a few hertz, sometimes 1 Hertz, 2 Hertz, 3 Hertz. Really special. So why is that? Because through the account of the magnetic induction, then the stator is stating, the rotor is rotating. Of course, the rotor speed will be really close to 3,600 RPM if we are using two poles, but not exactly 3,600, maybe 3,500, 3,400. But the rotor speed will be really close to the stator frequency of stator speed anyway. And then between them, that's how the rotor will see the magnetic flux will transfer. The magnetic flux rotating flux will be also using 60 Hertz. But the rotor itself rotating will be, of course, slightly less than 60 Hertz, maybe 59, 58. So the difference between them will be how the rotor will experience the magnetic flux. Because they run stationary, the field are rotating, interact with the rotor also rotating. So the one you see from the rotor itself will see much lower frequency. So that frequency will be induced on the rotor, become a much lower frequency, more look like relativity. When you're sitting on a rotor, the rotor is rotating, and then you see the magnetic flux outside you, and then you try to trace the magnetic flux, but your frame is also rotating at roughly about 3,600 RPM. So that's why what the rotor see or what the rotor current see will be much lower frequency because your whole environment is rotating. The rotating magnetic flux are rotating, and your rotor is also rotating. So what the rotor see from itself will be much lower frequency. And the rotor also experience much lower frequency. So that's so-called the slip. So that's something we also need to discuss more detail about what it look like. So that's why inside the rotor more look like a kind of the relativity, because they all relate to each other by some special frequency manner. But anyway, you can see that in here, the rotor bar are much thicker. This is a conducting current. This current, because we have short circuit there, so we need to have a much thicker rotor winding in order to accommodate such a large current. Inside current much larger because inside the frequency are also quite low. But low frequency, that is to say the skin effect will be not that demanding. For high frequency, as you know that high frequency, we got more eddy current. The lower frequency, we got less eddy current. So the lamination, we still need to use lamination, but not that demanding. We can use thicker lamination anyway. And the construction of the screw cage will be look like all this bar. So why is called screw cage? Because it just look like a cage. We put a screw inside. So the structure look like screw cage. I mean, in the old day when we using this kind of structure to confine the screw. So that's why this motor has been called a screw cage, because it really look like a screw cage. But inside is the lamination. Inside there, supposedly look like we have a screw inside. The rotor bar will be constructed in such a way, in more longitudinal manner. So inside this both end will be short circuit, shorten them, so it more look like equal to 1 turn for the rotor. So this structure will be simple, easier to maintain. We don't need to put many winding. You see, if we got a magnetic rotating part, we don't like to have too many winding inside because it's really difficult to make sure the winding will not get loose after many years. So that's why I can see that the stationary part is many winding because they're not moving, so we don't worry too much about it. But for rotating part, because we only have this bar, they're not winding. Actually, they are also copper bar or aluminum bar to do that. So that's why it's also quite robust. So that's why I can see that this able to produce us with a low maintenance, low cost, easier for the construction. But the main disadvantage will be for all the induction motor, the speed of rotation are not equal to the AC frequency. So AC frequency is 60 Hertz, but the induction motor rotating speed is not 60, it's slightly less than that. So that's why this kind of motor, we call them the asynchronous. They're not synchronous. So we have a synchronous machine with this called asynchronous. Asynchronous machine, that means the motor rotating speed is not equal to the input AC frequency. So the rotation speed are slightly lower than that. So that is to say the speed of rotation is uncertain. It can be close to 60 Hertz, can be 59, 58, 57, depend on the loading, depend on various situation. So that's why it's not easy to control the speed range. And also the starting torque also quite limited. Why is that? Because when we try to start a motor from zero speed, then the motor itself have the rotor is stationary. The input stator frequency will be 60 Hertz. So the induction between them will have a really low induction. The induction principle in here for the motor, later on we'll see a bit more about that. We like the stator and rotor have slightly low different in frequency, slightly different, not too high different. So that's slightly different, able to generate as a higher torque. But if between them will be so much different, the magnetic induction will have much less torque generated. So probably that will be see the equation from next few lecture. But here, then you can see that mainly about this kind of induction motor, the starting torque will be limited mainly about the induction principle. We cannot induce that kinetic force to the rotor properly. So that's one of the issues we can see from the rotor system. So we don't have 1 or 2 minutes, and before we go away, any question up to this point? So this lecture mainly we talk about the configuration for stator and rotor, use some basic principle, how they look like. And then after this set of lectures, we start to talk about the modeling, the formulation. That would be more interesting. Here will be just kind of the description, how the stator and rotor look like. And no question? So do come on time on Wednesday, our midterm, in person. Do bring your PC in case I haven't quite decided the MC will be online or offline. So if online, then you can key in your answers of the MC question into the canvas. And then we also written form, maybe do it on paper. Okay. So in case, then just bring your PC. All right. So see you again 6 p.m. on Wednesday.
Thank you.
Bye for now.
Oh, yeah.
Give me a second, let me repeat it.